So let's continue with this tutorial. So let me just recap what we've done so far. Is we are looking at the how changing one variable affects the other by looking at how the relationship between the two variables. So if you have the equation y is kx, for example, that means that this y is directly proportional to to x. So then that basically implies that if I double x, then this would mean that y also doubles, and if you have y is kx squared, where y is proportional to the square of x, then doubling x would mean that y is changed by the square of this factor here. So you will have to square that, which is going to be 4y in this case. And also this also implies that if you were to double y, if you were to double y itself, then how will that affect x by this relationship? This means that x would be the square root of 2, the original x. So that's what we're doing here. And also, if you have the inverse relationship where y is inversely proportional to x, then that means that if I were to double x, then how will my y change? Then my y will change by a half. So this would half, because it's an inverse relationship. And in the case where y is k over x squared, where y is inversely proportional to the square, then that if I were to triple x, let's say I change x to 3 times x, then how will this affect y? Then y would reduce by the square of the inverse of the change in x. So we'll have the inverse is 1 over 3, inversely proportional, and we'll have to square that, which would imply that y would change by 1 over 9, the original y. So that's basically what we are doing in this tutorial. So we will answer these questions the same way. 2.3. So you have the object with mass m and is dropped from height h above the ground. So then it hits the ground after time t, since it was dropped, and it hits it with a velocity v. So then 2.3.1, you want to determine the distance the object travels, the third of the total time since it was dropped. So what distance does this object travel? The approach here is that you will take the height above the ground as distance it travels for this duration of time t, and this velocity is the velocity it has after time t, since it was dropped, or the velocity it has when it has traveled distance h. So for 2.3.1, we must establish first the relationship that relates distance and time, and the kinematic equation. So we must ignore the effects of air resistance. So the kinematic equation here is v initial t plus half acceleration t squared and our displacement, the distance is h, and since it was dropped means that initial velocity is 0, and the variable delta t from the problem is just t, and we'll let acceleration be the gravitational acceleration. So then we have h is equal to this is the first term is 0 there, so it's half g t squared. So then what happens, so this equation means that h is directly proportional to the square of time. So then if I reduce t by a third, how will that affect my h? So we'll what we want to determine is that if this h is our distance that is traveled by the object during this time interval, then what we want is that if we reduce the time to a third, we want what distance is it going to travel. So we must express this in terms of h. So we just want to determine the factor f that gives us the new in terms of h, the new distance. So the question is, what is this factor? So when we look at this relationship that h is proportional to the square of t, then if you reduce t to a third, then then this means that your h is going to be also reduced by the square of that because of the square. So this is going to be a third or squared. Okay, so this is our new h there. So then our factor is equal to 1 over 3 to the power 2 is 1 over 9. So our factor is equal to 1 over 9. So therefore h prime is 1 over 9 h. You can also approach this problem mathematically, just using the equations that okay, if I have h, so this is an or, h as half g t squared, then if I have my t prime is equal to 1/3 t, and my h prime is also going to be half, and I'll copy the other ones that I'm not changing, so the assumption is not changing. So now what is the new distance in terms of the new time? Then that is going to give me h prime is, I'll just substitute the change I made in t. So the change I made is I reduced this to what, third of t. So then there should be a square there. So then the h prime there is a third, is half g. Third squared is 1 over 9 t squared. And when they say in terms of h, so you will you want to have this in the next step. So how do you do that? You just just place this 1 over 9 in front, then you have 1/2 gt squared, and you've already declared that h is half gt squared. So the new prime h prime is 1 over 9 h. Okay, so which gives us the same answer as that one there. And then let's look at the velocity. So that's 2.3.2. 2.3.2. So now we must first write the relationship between velocity and distance, ignoring the effects of air resistance. So the kinematic equation here is v final squared is equal to v initial squared plus 2 g delta y. And so this v final is just v. So this is our v squared here, is equal to the initial velocity 0, so that's 2g, and our delta y is h. Okay, so now this says that the square of velocity is the one that's proportional to h. Okay, so what happens when you change h to h over 4? I think it's easy if you write this as the square root of 2gh, so that you know that the velocity itself is proportional to the square root of h. So then if I change h to h over 4 to a quarter, then the velocity, the new velocity, let me just write this actually this way here. So the velocity itself is going to change by the square root of this factor. So it's going to change by the square root of 4. So that means that the square root of 4 is going to be 1 over 2 v. So then the new velocity, which is in terms of the original velocity, so we've determined our factor as 1 over 2. So then the new velocity is 1 over to the half the original velocity if you change the distance by a quarter, noting that the velocity is proportional to the square, so to the square root of h. Again, you can just apply just equations. You can simply apply the kinematic equations and start with the fact that v is the square root of 2gh from above, and now that means then that v prime is equal to the square root of 2g h prime. So then if you have your h prime as h over 4, then when you substitute for h prime there, you'll get 2g, and you have h over 4 here. So then that's equal to square root of 2gh over the square root of 4, which is h over 2. No, which is yeah, square root of so v prime is the square root of 2g h over 2, and you've declared that square root of 2gh is v. So then that means that your v prime is 1/2 v. Okay, so then let's look at question 2.4. You can try this by yourself again. You can pause this video and then you do this one. So you have planet X, which is has 3 times the mass of the planet Earth, and its radius is twice that of planet Earth. So then if you let the gravitational acceleration on Earth's surface be g, then what will be the gravitational acceleration on the surface of planet X in terms of g? And 2.4.2, you can use this one to calculate the weight of what's the value of the weight of a mass of 65 kilograms. Again, here the first step, of course, is that you must write the gravitational acceleration, so the equation for that on the planet's surface. So you write that equation which relates the mass of the planet and its radius, and then determine the new g. If you change the mass by 3, so if the new mass is 3 times the original mass, and if the radius is twice the original radius, so how will that affect? So you can calculate a factor that that will change, that g will change by. Okay, so you can pause the video and do that, and then come back and view my solutions. Right, so what you should have gotten is so your first step is on the surface of a planet. The equation is g m, so I'm going to call this ge, and me over re squared, and then what happens when you change the mass? So I think at this point actually you can just deduce the factor by noting that g is directly proportional to the mass. So if I change the mass 3 times, so g will also be 3 times as much. And if I double the radius, then since g is inversely proportional to the square of g, so then this will reduce by 1 over 2 squared, so g will reduce by a quarter, so then the new g will just be 3/4 of the original g. But I'm just going to write the calculations down. Okay. Here is that the first one is that you 3 times e, so vector is going to be 3 because of the direct proportion, and then the inverse proportion, and then what did we do? We doubled the radius, so the inverse proportion, this is going to be reduced by the square, and so the factor is going to be 3 over, so this is 1 over 4, so that's 3 over 4, so then gx is 3/4 of the original g. Okay, and of course you can also do it mathematically. Just have g as gme over re squared, and then have your gx as gmx over rx squared, and then mx is 3me, then rx is 2re. So then when you substitute these in the equation for gx, you have gx is g, and then you put 3me divided by 2re all squared, and then that is equal to 3g me over 4re squared, and then that gives you 3 over 4 gme over re squared, which is 3 over 4 original g. So so that's how you can also do that one. Then so if you have the mass of 65, so you want the weight, so for 2.4.2, you note that weight is equal to mg, so we know that g is 9.8, so that's 9.8. So on this so on this, let me put mge here, but we don't want its weight on planet Earth, we want it on the planet X. So GE is 9.8 meters per square second. So then the weight of this object, so this is its weight on E. So the weight of this object on planet X is going to be its mass times 3/4. So the GX is going to be 3/4 GE. So that gives us 65 times 3/4 of 9.8. Okay, then that's equal to, so you can plug this in your calculator, and then we have 65 then the times 0.75 times 9.8, which is equal to so that is equal to okay, let's do this. I don't know what happened there. Right, so this so that weight E. Okay, so the weight is 477,75 newtons. So that is the numerical value is 477,75. Of course, you could have calculated it this way: weight on Earth as 65 times 9,8, right? And then so that is basically approximately 650. So let me do that here. So I could have 65 times 9,8, and then what will that give me? So the weight on Earth would be 637 newtons there, and then then this 637, so would have this 600 637, then you multiply this by 3/4 to get your answer. Then the weight, so the weight on this planet, weight on planet X is going to be 3/4 the weight on planet E, so which is 3/4 times 637, which would give you 477,75 is the numerical value of the weight. All right, so I hope you can see that now these problems are a bit easier now, so we can move on to question 3, exercise 3, using the same approach, but I'll do that in the next video. Thank you for listening. I'll see you in the next video.